Hey there, y'all. Today we're going to look at the review for the Chapter 1 test. What I've compiled here in this document is all of the student will be able to statements from each section. I'm going to briefly go over what each statement is about, reviewing what we've talked about in this chapter, reference you back to the lessons that we've looked at, and then kind of close out with what are the big things you need to know for this test. So let's start with sections 1 and 2. In section 1 and 2, that was on solving linear equations and linear inequalities. And so remember that we can translate verbal expressions into algebraic expressions and equations and vice versa. We can solve equations using the property of equality and solve one- and multi-step inequalities. And so when we look at that section, remember we talked about translating, right? So how can I take a statement and those word phrases like less than or increased by or product or quotient, all those terms that we talked about in section 1, how can I take it from a verbal expression to algebraic or vice versa, right? So how do I take it from an algebraic statement like 7 equals negative 2 plus x and write it out as a verbal statement? Then we looked at the properties of equality. Remember, we have the reflexive, symmetric, and transitive properties. Reflexive just means that a number is equal to itself. Symmetric means that I can switch the two sides of the equal sign and it stays the same. And transitive, remember, is the property where if A is equal to B and B is equal to C, then A is equal to C. We can cut out the middleman, right? And so substitution, finally, remember, if I have that A is equal to B, I can replace it with an equivalent value. And that's what we see there. Okay? So we looked at the different properties and how to identify them. We talked about the properties of equality for us to be able to solve equations. And so that's, if I add something to both sides of an equation, it keeps it balanced. Or if I multiply something to both sides of an equation, it keeps it balanced. Remember, the only caveat is that you cannot divide both sides by 0. That causes issues. Okay, so we looked at how to solve equations, and all of this is old stuff from Algebra 1. How to solve for a variable. Remember, that is, I got to get that variable completely by itself using our order of operations to undo all those. We looked at the properties of equality. And like these statements here, how can I change the statement so that it's equal to a different value so I can get its solution? And then finally, we looked at inequalities. And remember, we need to have either a dot or a circle. Which way is our shading going to go in our final solution set? Okay. And so that was all of section 1. We had a word problem at the end of this section. But that was all of section 1. Again, dealing with equations and inequalities and the properties that allow us to solve them. So in 1.3, we talked about rate of change and slope. And our two students will be able to standards or statements were that you can find the rate of change and determine the slope of the line. And remember, we talked about in section 1.3 about the slope formula, right? M is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we talked about how rate of change is dealing with that in certain portions, right? Slope is of a line, that's a straight line on the graph. Rate of change between any 2 points, what is the change between them? And we use our slope formula to do that. Or, remember, we also talked about using the delta y over delta x. And remember, delta means the change of or the change in. And remember, we can use our coordinates to find the slope. And we can find it from a graph. Remember, this was a pretty short section because, again, most of this is from 8th grade math and Algebra 1. Most of this was review, but that was what we had there. As we looked at 1.4, we looked at writing linear equations, with our statements being that we could write an equation of a line given the slope and point on the line, and write an equation of a line that is parallel or perpendicular to a given line. So when we looked at 1.4, remember that we talked about slope-intercept form, y is equal to mx plus b. How can we write the equation of a line from that if I'm given a slope and a point? Or if I'm given 2 points, how can I find the slope first and then be able to write the equation? We also talked about point-slope form, which is here. Y minus y sub 1 is equal to m times x minus x sub 1. And remember, the x1, y1 is a coordinate on the plane, on our line. And our slope, of course, is the slope of the line. And so we looked at examples here. and you'll see that stuff has kind of shifted down a little bit in the notes, but everything should shift back up. So if I'm given 2 points, remember best thing to do, label it x1, y1, x2, y2, find the slope first, then work your way through point slope form first, right? And then work your way through to get it to slope intercept form. And then we can talk about parallel and perpendicular lines. Remember that 2 non-vertical lines are parallel if and only if they have what? The same slope, right? And we see here the 2 parallel lines. Remember that perpendicular lines are only perpendicular if and only if the product of their slopes is -1. And we get that because if I take one fraction and I have its opposite reciprocal, opposite meaning that you change the sign, positive to negative or vice versa, and reciprocal meaning that you flip that fraction, then we're going to get that -1. And so we see here like 3 and -1/3 are perpendicular. Or if I had like -2/3 and +3/2, those would be perpendicular slopes. Okay? And we looked at how to write the lines based on those. So that's section 1.4. So in section 1.5, we talked about graphing linear inequalities, and our standard there, our statement there was that we should be able to graph and apply linear inequalities. And so when we look at some of the problems here, remember that when we graph linear inequalities, we have our line, and that line can either be solid or dashed, right? And then we got to determine where's the shading going to be. Is it above the line or is it below the line? Remember that our best checkpoint is 0, 0. If that works, I shade where the origin is. If it doesn't work, I'm going to shade the opposite side of the line. Again, make sure you test your points, have your shading in the right spot, and remember that graphing involves shading when we deal with inequalities. We looked at some word problem examples of this as well, and we talked about how we could graph that on the coordinate plane and get the points that we need and find possible solutions in that area. Or remember that the solutions are also on solid lines, but not on dashed lines. Okay, so that's section 1.5. So in section 1.6, we looked at solving systems of equations, and we looked at how to do that both graphically and algebraically. And algebraically means that we did it with substitution and elimination. And so let's look at section 1.6. When we looked at here, remember we talked about all the different methods, and we talked about how about matrices and Cramer's rule would be methods that we'll look at later on. We could solve with a table, but a table's really not an effective method. It is if the values are very easy and the solution's very easy to get to. But remember we talked about graphing and how we're looking for the point of intersection. But remember, if they're parallel, there is what? No solution. And if they're the same line, there are infinitely many solutions, and those solutions are along that line that's paired together. And so then we looked at consistent and inconsistent systems, and remember consistent systems have at least one solution. So that means that it's either going to be an intersecting system or it's going to be a same line system because they have at least one solution. An inconsistent system is one that has no solutions, meaning the only type of system that's inconsistent is one where the lines are parallel. And remember, if a system has exactly one solution, it's consistent, but we'll also use the word independent, right? And if it has infinitely many solutions, then it is consistent because it has at least one, but it's dependent because they're infinitely many, okay? And so we looked again at some more examples of how to classify those. And then we looked at our algebraic methods. Substitution. Remember to solve for one variable, substitute that in, solve for that second variable. So now you're going to get that one of the variables is equal to a number. You're going to find that value, plug it back into an original equation, and that'll get you your ordered pair. Now remember, if everything cancels and you get like 0 equals 0, then we have infinitely many solutions because it's a true statement. And if I get that 0 is equal to like 5, that's a false statement and there's no solution. And so again, we look at the problems here and where we can set up our equations. Remember, especially with the word problems, typically one equation will be based just on the number of items. So it's normally like x plus y is equal to a number. And then our second one, typically a lot of times with cost. So you'll have the cost times the number that you buy, that's a variable like x, plus the cost of the second one, plus the number that you buy, that's the y, equals to the total amount that you spend. Okay? Keep that in mind as you're looking at these statements. Remember, elimination is that you'll multiply one or both equations by something if the coefficients are not the same or they're not opposites. And if they're the same, then you want to multiply one line by -1. You'll add those equations together, unless you have them the same and you want to subtract. That's up to you. Eliminate the first variable. That'll let you solve for the second. And then substitute that back in to find the one that you eliminated originally. Okay? And there's examples of those here. Okay, so that is section 1.6 on solving systems of equations. We then looked at 1.7 on solving systems of inequalities. And we said that we would want to solve systems of inequalities graphically and then determine the coordinates of the vertices of a region formed by the graph of a system of inequalities. And so in this section, there was two major things. Right? We first talked about how we just graph those on the coordinate plane. And remember, that goes back to what we did in section 1.5. How do I graph a linear inequality on the graph? But then how do I graph a second one on that same coordinate plane? And where do those shadings interact? And remember, we talked about how red and blue make what? Purple. So we're looking for that final purple region to be our solution area of this system. And so again, like we'll see here, we graph the one, we graph the other, and we have our purple region that came out here. And remember, there's only red up here, there's only blue down here, there's nothing over here, so those are not solutions. And remember, on the lines, if it's a solid line touching our final region, our feasible region, then that is a solution. But if it's a dashed line and it's touching our feasible region, then it's not a solution. And so again, points along this red line would be a solution, but points along the blue would not. And the point of intersection here, because one line is dashed, it's not a solution. Okay? Everything in the purple range, of course, is a solution. We also looked at word problems with these. We saw some systems where we get no solution, and then we looked at word problems and how can I graph through these. And again, it's reading through the problem, understanding which inequality we have and how we're going to set it up and set up which variable is x, which variable is y, how we're going to get this on the coordinate plane. So that is section 1.7. Our final section that we just looked at was on 1.8 on optimization with linear programming. And so remember that the I can statements in this section were that you'll be able to find the maximum and minimum values of a function over the region, and that you'll be able to solve real-world optimization problems using linear programming. And so in this section, remember that we talked about using all of our graphs together, getting it graphed, and finding where it finally overlaps. Okay? Now, I'm going to give you a little help on this on the test. On a problem like this, I will already give you the graph with the feasible region shown. So that way you don't have to graph everything. Because what I want to test in this section is I want to test on how to find our mins and maxes. Okay? So those graphs will already be given to you for problems where we're doing optimization. You will not get that luxury for the stuff in 1.7 on solving systems of inequalities and solving systems of equations. You will have to graph those lines for those two sections. And so think about what you're going to get out of these to be able to get your maxes and your mins. So that's all of Chapter 1 in a nutshell. You're going to have a Google form that I'm going to ask you to fill out for this review video. There's no questions in it like the normal lesson videos. The only thing that will be there is that, yes, you have watched this video, and if you have any questions from any of the sections that you want to go over in class. So that's what I ask you to do. If you got any questions you want to go over, or any sections that you want to go over problems from, or like from your work assignments or from the quizzes, we'll look at all those. And again, put those questions in the Google form, and that is all for today, and I'll see y'all next time.